Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about conservation of momentum. Conservation of momentum is similar in spirit to conservation of energy, which we've previously discussed, and it rightly takes its place alongside conservation of energy as one of the guiding principles, not only of the material in Physics 107, but also throughout the various realms of physics. Ideas about momentum are particularly important when one begins to study situations that involve systems of particles. Up until this point in Physics 107, our discussion has primarily, almost exclusively, dealt with situations in which the system under study was a single particle which moved with a single velocity at any one time. And now we're going to expand that. We're going to talk about situations in which there are multiple particles or objects in which different parts of the object are moving at different velocities. And we'll see that ideas about momentum are absolutely essential when you begin to study such systems. So let's dig in. So let's start by talking about systems that just have a single particle. That's what we've been talking about exclusively so far. So in particular, let's talk about Newton's second law for a single particle, like so. So for a single particle, we can write that the net force on the particle is equal to the mass of the particle times its acceleration, which I will write as dv dt, the rate of change of velocity. And if the mass of the particle is a constant, I can rewrite this expression as F net is equal to the time rate of change of m times v, like so. And we can define the momentum of the system. Single particle system is just the mass of the particle times its velocity. And so now with this definition in hand, we can just rewrite Newton's second law as F net equals dp dt. And this is, you can just think of this as an alternate form of N2 involving this new quantity that we've defined as the momentum. And this relationship gets the barest of mentions in the Wolfson text so far. It's mentioned briefly in chapter 4, and I think I've held off talking about momentum almost exclusively in Physics 107 so far, because if you're talking about systems of single particles, it doesn't really bring that much to the table to talk about momentum. Talking about the second law the way we've done so far in terms of this familiar form has been totally adequate. But now, as I said, we're going to begin to talk about systems of particles, and there talking about the momentum, the ideas about momentum are going to become essential. So before we get into systems of particles, though, let's just talk a little bit about what momentum is and try to develop a little bit of intuition about what momentum is. So for the case of a constant force, it's easier to think about in that case. So for F net just being equal to a constant, we can write that F net is equal to the ratio of the change in momentum divided by the time interval over which that change occurs, or the change in momentum is equal to the force, this constant force, times time interval. Okay, so this form is a good form to think about to begin to develop an intuition about what momentum is, because what it says is that momentum is something that can be changed by a force acting over time. So think about an object that has some initial momentum. That is, its momentum, its mass times its velocity. Maybe it's a train, and the train has a big mass and a certain velocity, and it's coming towards you, and you want to change its momentum. Let's say you want to bring it to rest. So you're going to have to exert a force over time, and the bigger the change in momentum that you want to cause to occur, the bigger the force and or the longer the amount of time it's going to take in order to stop that train. So you can think of momentum. This is sort of the popular meaning of the word. If something has momentum, it's something that's hard to stop. A candidate has momentum because they've won a number of primaries in a row, and we say that candidate has momentum. They're hard to stop. Well, the physics meaning of the word momentum is exactly in that sense. Something with a big momentum is sort of hard to stop, and it's going to take a big force acting over a large amount of time to bring that object from a state of big momentum to, say, a state of zero momentum. So just for the system consisting of a single particle, we already see something emerging with momentum that mirrors something that we've previously seen in our discussion of energy and what we call the energy principle. So with the energy principle, we had a way of calculating the energy of a system. So we divided the world into system and surroundings, and the way we calculated the change in the energy of the system was there was this quantity that we called work. Work was a scalar quantity, energy is a scalar quantity, and we calculated the work in the simple case of a constant force by just the constant force exerted by the surroundings on the system, and it's just the scalar product of that force with the displacement that gave the work. So now if you look at, again, just considering a single particle, the way we calculated changes of momentum of that system, the rule is that we take the force exerted by the surroundings and we just multiply it by the time. So we have a vector force times a scalar time. We get a vector quantity here, which we call the impulse. So the impulse is this quantity. The force times the time interval is the way we calculate the change in momentum of the system. So we can say that, just to summarize, work done on a system by the surroundings causes the energy of the system to change. An impulse delivered to a system causes the momentum of that system to change. And while we've shown this just for the simple case of a system of a single particle and constant force, that same basic structure will extend to multi-particle systems. And now let's suppose we consider an isolated system, by which we mean there is no interaction with the surroundings. Well, for an isolated system, in the case of energy, there was no work done on the system, so the energy of the system doesn't change. And similarly, for an isolated system, there's no impulse delivered to the system. So for an isolated system, the momentum of the system doesn't change. So we have, for the case of isolated systems, these great conservation laws. Conservation of energy means no interaction with the outside world. The energy of the system remains constant. It is conserved. And similarly, if you have an isolated system, the momentum of that system is also conserved. Okay, now to see where momentum really becomes essential is when you begin to consider systems that consist of multiple particles. And the main feature to focus on in a system of multiple particles is that now there is the possibility that different particles can have different velocities. So, if you try to write n2 as in the familiar way, if you write n2 as F net equals m dv dt, what do you put in for v, or what do you put in for m for that matter? It doesn't really even make sense because there's not a single velocity associated with the particles in the system, nor is there a single mass. So this doesn't really work. We need a new way to deal with this situation, and that way is to involve momentum. So we are going to define the momentum of the ith particle as just the mass of that ith particle times its velocity. And now we can define the momentum of the system, and Wolfson uses an uppercase P when talking about the momentum of a system, and that is just going to be defined as the sum of all the individual momenta like that. So it's just a sum of the mass of the ith particle times the velocity of the ith particle. And the way we write Newton's second law in this case is that the external force, the net external force acting on the system, is just equal to the rate of change of the momentum of the system, dp system dt. So here's a situation I have in mind. It's a cold winter's day. Lake Waban has frozen over, and I am standing with my ice skates on, holding a copy of the Wolfson text in my hand, and myself and Wolfson are at rest, and that constitutes our system. And this is an isolated system. I'm going to assume that there are no meaningful interactions with the outside world. And then I am going to, in frustration, hurl my Wolfson text to the right with a certain velocity. And the question is, what happens to me when I do that? So, a bit more abstractly, we can say that my system consists of two particles, and in the initial state, both the particles have zero velocity. So that means that the total momentum of the system initially is zero because each of the individual momenta of the particles that make up the system are zero. So clearly, when you add a bunch of zeros, you get zero. So the system has an initial momentum of zero. And since it's an isolated system, that momentum will be conserved. So even after I throw the book, we expect that the total momentum of the system will be zero. So that means if I throw my book to the right, that way, I am going to acquire a velocity to the left so that the total momentum of the system remains zero, like so. So this is just a simple example, but it really underscores lots of important things, like, for example, the way rockets work, which will be the topic of a forthcoming episode of What's the Big Idea? So that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye bye.